Chapter 4 of 20th Century Inventions, A Forecast. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Esther. 20th Century Inventions, A Forecast by George Sutherland. Chapter 4 Artificial Power. The steam turbine is the most clearly visible of the revolutionary agencies and motors using the artificial sources of power. In the first attempts to introduce the principle, the false analogy of the water turbine gave rise to much waste of inventive energy and of money. But the more recent and more distinctly successful types of machine have been constructed with a clear understanding that the windmill is the true precursor of the steam turbine. It is clearly perceived that, although it may be convenient and even essential to reduce the arms to pygmy dimensions and to enclose them in a tube, still the general principle of the machine must resemble that of a number of wind motors all running on the same shaft. It has been proved, moreover, that this multiplicity of minute wheels and arms has a very distinct advantage in that it renders possible the utilisation of the expansive power of steam. The first impact is small in area but intense in force, while those arms which receive the expanded steam further on are larger in size and suited to making the best use of a weaker force distributed over a greater amount of space. The enormous speed at which steam under heavy pressure rushes out of an orifice was not duly appreciated by the first experiments in this direction. To obtain the best results in utilising the power from escaping steam, there must be a certain definite proportion between the speed of the vapour and that of the vane or arm against which it strikes. In other words, the latter must not smash the jet, but must run along with it. In the case of the windmill, the ratio has been stated approximately by the generalisation that the velocity of the tips of the sails is about 2½ times that of the wind. This refers to the old style of windmill as used for grinding corn. The steam turbine must, therefore, be essentially a motor of very great initial speed, and the efforts of recent inventors have been widely directed in the first instance to the object of applying it to those purposes for which the machinery could be coupled up to the motor with little, if any, necessity for slowing down the motion through such appliances as belting, toothed wheels, or other forms of intermediate gearing. The dynamo for the electric lighting naturally first suggested itself, but even in this application it was found necessary to adopt a rate of speed considerably lower than that which the steam imparts to the turbine, and unfortunately it is exactly in the arrangement of the gear for the first slowing down that the main difficulty comes in. Nearly parallel is the case of the cream separator, to which the steam turbine principle has been applied with a certain degree of success. By means of fine flexible steel shafts running in bearings swathed in oil, it has been found possible to utilise the comparatively feeble force of a small steam jet operating at immense speed to produce one of much slower rate but enormously greater strength. Some success has been achieved also in using the principle not only for cream separators, which require a comparatively high velocity, but for other purposes connected with the rural and manufacturing industries. An immense forward stride, however, was made when the idea was first conceived of a steam turbine and a water turbine being fixed on the same shaft, and the latter being used for the propulsion of a vessel at sea. In this case it is obvious that, by a suitable adjustment of the pitch of screw adopted in both cases, a nice mathematical agreement between the vapour power and the liquid application of that power can be ensured. All previous records of speed have been eclipsed by the turbine-driven steamers engined on this principle. Through the abolition of the principal causes of excessive vibration, which renders dangerous the enlargement of marine reciprocating engines beyond a certain size, the final limit of possible speed has been indefinitely extended. The comfort of the passenger, equally with the safety of the hull, demands the diminution of the vibration nuisance in modern steamships; and whether the first attempt to cater for the need by turbine engines be fully successful or not, there is no doubt whatever that the fast mail packets of the future will be driven by steam engines constructed on a system in which the turbine principle will form an important part. Further applications will soon follow. It is clear that if the steam turbine can be advantageously used for the driving of a vessel through the water, then conversely it can be similarly applied to the creation of a current of water or of any other suitable liquid. This liquid current again is applicable to the driving of machinery at any rate that may be desired. In this view the slowing down process, which involves elaborate and delicate machinery, when accomplished in the purely mechanical method, can be much more economically effected through the friction of fluid particles. One method of achieving this object is an arrangement in which the escaping steam drives the turbine shaft running through a long tube and passing into the water in a circular tank, in which again the shaft carries a spiral or turbine screw for propelling the water. The arrangement, it will be seen, is strictly analogous to that of the steam turbine as used in marine propulsion, the shaft passing through the side of the tank just as it does through the stern of the vessel. One essential point, however, is that the line of the shaft must not pass through the centre of the circular tank, but must form the chord of an arc, so that when the water is driven against the side by the revolution of the screw, it acts like a tangential jet. Practically the water is thus kept in motion just as it would be if a hose with a strong jet of water were inserted and caused to play at an obtuse angle against the inner side. Motion having been imparted to the fluid in the tank, a simple device, such as a paddle wheel immersed at its lower end, may be adopted for taking up the power and passing it on to the machinery required to be actuated. By setting both the shaft carrying the vanes for the steam turbine and the screw for the propulsion of the water at a downward inclination, it becomes practicable to drive the fluid without requiring any hole in the tank; and in this case the latter may be shaped in annular form and pivoted so that it becomes a horizontal flywheel. Obstructing projections on the inside periphery of the annular tank assist the water to carry the latter along with it in its circular motion. For small steam motors, particularly for agricultural and domestic purposes, the turbine principle is destined to render services of the utmost importance. The prospect of its extremely economical construction depends largely upon the fact that, with the exception of 2 or 3 very small bearings carrying narrow shafts, it contains no parts demanding the same fine finish as does the cylinder of a reciprocating engine. It solves in a very simple manner the much vexed problem of the rotary engine, upon which so much ingenuity has been fruitlessly exercised. The steam turbine also has shown that, for taking advantage of the generation and the expansive power of steam, there is no absolute necessity for including a steam-tight chamber with moving parts in the machine. For very small motors suitable for working fans and working other household appliances, the use of a jet of steam applied directly to drive a small annular flywheel filled with mercury, without the intervention of any turbine, will no doubt prove handy. But in the economy of the future such appliances will take the place of electrical machinery only in exceptional situations. One promising use of the turbine or steam jet, used to propel a flywheel filled with liquid as described, has for its object the supply of the electric light in country houses. In this case the flywheel is fitted on its lower side to act as the armature of a dynamo, and the magnets are placed horizontally around it. The full effective power from a jet of steam is not communicated to a dynamo for electric lighting or other purposes unless there be a definite ratio between the speeds of the turbine and of the armature respectively. This may be conveniently provided for with more precision and in a less elaborate way than that which has just been described, if the steam jet be made to drive a vertically pendant turbine, the lower extremity of which, carrying very small horizontal paddles, must be inserted into the centre of a circular tank. The principle upon which the reduction of speed necessary for the dynamo is then effected depends upon the fact that in a whirlpool the liquid near the centre runs nearly as fast as that on the outer periphery, and therefore, the circles being so much smaller, the number of revolutions effected in a given time is much greater. Thus a steam jet, turning a pendant turbine, dipping into the middle of the whirlpool, and carrying paddles at an enormously high speed, may be made to impart motion to the water in a circular tank, or, if desired, to the tank itself, at a very much slower rate, the amount of the reduction, of course, depending mainly on the ratio between the diameter of the tank and the length of the small paddles at the centre setting the liquid in motion. For special purposes it is best to substitute a spherical for an ordinary circular tank, and the size may be greatly diminished by using mercury instead of water. The sphere is complete, excepting for a small aperture at the top for the admission of the steel shaft of the steam-driven turbine. No matter how high may the speed, the liquid cannot be thrown out from a spherical revolving receptacle constructed in this way. Moreover, the mercury acts not only as a transmitter of the power from the turbine to the purposes for which it is wanted, but also as a governor. Whenever the speed becomes so great as to throw the liquid entirely into the sides of the sphere, so that the shaft and paddles are running free of contact with it in the middle, the machine slows down, and it cannot again attain the full speed until the same conditions recur. The rate of speed which may be worked up to as a maximum is determined by the position of the paddle wheel, which is adjustable and floats upon the liquid, although controlled in its circular motion by the shaft which passes through a square aperture in it, and also a sleeve extending upward from it. The duty of the latter is to economise steam by cutting off the jet as soon as, by its rapidity of motion, the paddle wheel has thrown the mercury to the sides to such an extent as to sink to a certain level in the centre. Cheap motors, coupled with cheap dynamos, will, in the 20th century, go far towards lightening the labours of millions whose toil is at present far too much of a mere mechanical nature. The dynamo itself, however, requires to be greatly reduced in first cost. Particularly, it is necessary that the expense involved in drawing the wire, insulating it, and winding machines with it, should be diminished. This will no doubt be partly accomplished by the electrolyte producers of copper when once they get properly started on methods of depositing thin strips of wires of tough copper on to sheets of insulating material for wrapping round the magnets and other effective parts intended for dynamos. There is no fundamental reason which forbids that when electrode deposition is resorted to for the recovery of a metal from its ore, it should be straightway converted to the shape and to the purpose for which it is ultimately intended. This consideration has presented itself to the minds of some of the manufacturers of aluminium, who make many articles intended for household use electrolytically, and it must affect many other trades which are concerned in the output in the working up of metals readily susceptible of deposition, more particularly such as copper. The familiar aneroid barometer furnishes a hint for another convenient form of small steam engine. In seeking to cheapen machinery of this class, it is of the utmost importance that the necessity for boring out cylinders and for planing and other expensive work should be avoided. In the aneroid barometer a shallow circular box is fitted with a cover, which is corrugated in concentric circles, and the pressure of the superincumbent air is caused to depress the centre of this cover through the device of partially exhausting the box of air, and thus diminishing the internal resistance. To the slightly moving middle part of the cover is affixed a lever which actuates, after some intermediate action, the hand which moves on the dial to indicate, by its record of variations in the weight of the atmosphere, what the prospect of the weather may be. In the aneroid form of the steam engine, the cylinder is immediately widened and flattened, and the broad circular lid, with its spiral corrugations, takes the place of the piston. The rod, which acts virtually as a piston rod, is hollow, and it works into a bearing which permits the steam to escape when the extreme point of the stroke has been reached into a separate condensing chamber kept cool with water. The boiler itself, with corrugated top, may take the place of the cylinder. In some respects this little machine represents a retrograde movement even from Watt's original engine with its separate condenser, but its extreme economy of first cost recommends it to poor producers. In the near future no country homestead will be without its power installation of one kind or another, and there is room for many types of cheap motors. A motor like the steam turbine is evidently the forerunner of other engines designed to utilize the force of an emission jet of vapour or gas. There are very many processes in which gases generated by chemical combinations are permitted to escape without performing any services, not even that of giving up the energy which they may be made to store up when held in compression in a closed vessel. The reciprocating forms found suitable for steam and gas engines are hardly adaptable for experiments in the direction of economizing this source of power, one fatal objection in the majority of cases being the corrosive effects of the gases generated upon the insides of the cylinders and other working parts. As soon as the force of the emission jet can be applied as a factor in giving motive power, the fact that no close-fitting parts are required for the places upon which the line of force impinges will alter the conditions of the whole problem. In the centrifugal sand pump, as now largely used for raising silt from rivers and harbours, the serious corrosive action of the jet of sand and water upon the inside of the pump has been successfully overcome by facing the metal with Indian rubber, but nothing of the kind could have been done if the working of the apparatus had depended on the motion of close-fitting parts, as in the ordinary suction or lift pump. As an instance of the class of work for which gaseous jets, for driving turbines or similar forms of motor, may perform useful services, the case of farm-made superphosphate of lime may be cited. By subjecting bones to the action of sulphuric acid, the farmer may manufacture his own phosphatic manures for the enrichment of his land, but the carbonic dioxide and other gases generated as the result of the operation are wasted. Therefore, at present, it pays better to carry the bones to the sulphuric acid than to reverse the process by conveying the acid to the farm where the bones are a by-product. So bulky are the latter, however, that serious waste of labour is involved in transporting them for long distances. Calculations made out by the experts of various state agricultural stations show that, as a general rule, it is now cheaper for the farmer to buy his superphosphates ready made than to make them on his farm. The difference in some cases, however, is not great, and only a comparative trifle would be needed in order to turn the balance. This may probably be found in the economic value of the service rendered by a turbine engine or other device for utilizing the expansive power of the gases which are driven from the constituents of the bones by the action of the sulphuric acid. For pumping water and other ordinary farm operations the chemical gas engine will prove very handy, and the great point in its favour will be that, instead of useless cinders, the refuse from it will consist of the most valuable compost with which the farmer can dress the soil. Enamelled iron will be employed for the troughs in which the bones and acid will be mixed, and a cover similar to that placed over a Papin's digester will be clamped to the rim all round, the gases being liberated only in the form of a jet used for driving machinery. For very small motors, applicable especially to domestic purposes such as ventilation, there is one source of power which in all places within the reticulation areas of waterworks may be had practically for nothing. Probably when the owners of water supply works realize that they have command of something which is of commercial value, although hitherto unnoticed, they will arrange to sell not only the water which they supply, but also the power which can be generated by its escape when utilized, and by the variations in the pressure from hour to hour, and even from minute to minute. The latter, for such purposes as ventilation for instance, will no doubt come to the front sooner than the intermittent power now wasted by the outflowing of water, a power which is comparatively too small an item in most cases to compensate for the outlay and trouble of arranging for the storage of energy. But in the case of the variation in the pressure, without any escape of water at all, no such disability appears. Experiments conducted in several of the larger cities of England with various types of water meters, which are really motors on a small scale, have proved the practicability of obtaining a source of constant power from what may be termed the ebb and flow of pressure within the pipes of a water supply system. At every hour of the day there is a marked variation in the quantity of water that is being drawn away by consumers, and consequently a rise and fall in the degree of pressure recorded by the meter. In an apparatus for converting the power derivable from this source to useful purposes, something on a very small scale analogous to that which has already been described in connection with utilizing the rise and fall of a wave will be found serviceable. A small spur wheel is gripped on two sides by two metal lathes, with edges serrated like those of saws, and held against the wheel by gentle pressure. Every movement of the two saws, whether backwards or forwards, is then responded to by a continuous circular motion of the wheel, with the sole exception of those movements which may be too small in extent to include even as much as a single tooth of the wheel. On this account it is important that the teeth should be made as numerous as possible, consistently with the amount of pressure which they may have to bear. Resort may be had to the principle of the aneroid barometer in order to secure from the water within the pipe system the energy by which these saw-like bands are driven up and down with reciprocal motion. A very shallow circular tank in the shape of a watch is in communication with the water in the pipes, and its top or covering is composed of a concentrically corrugated sheet of finely tempered steel. At the centre of this is fixed the guide which pushes and pulls the saw-like lathes. Every rise and fall in the pressure of the water now effects a movement of the spur wheel, and the latter may conveniently be connected with the strong spring of a clockwork attachment, so that the water pressure is really used for winding up a clockwork ventilating fan. In the making of cheap steam and gas engines, as well as in machine work generally, rapid progress will be made when the possibilities of producing hard and smooth wearing surfaces without the need for cutting and filling rough cast metal have been fully investigated. Many parts of machinery will be electro-deposited, like the small articles already mentioned, in aluminium or hard copper at the metallurgical works where ore is being treated for the recovery of metal, or even at the mines themselves. Side by side with this movement there will be one for developing the system of stamping mild steel and then tempering it. At the same time also the behaviour of various metals and alloys, not only in the cold state but also at the critical point between melting and solidification, will be much more carefully studied, so as to take advantage of every means whereby accurately shaped articles may be made and finished in the casting. It has been found, for example, that certain kinds of type metal, if placed under very heavy pressure at the moment when passing from the liquid to the solid condition, not only take the exact form of the mould in which they are placed, but also become extremely hard by comparison with the same alloy if permitted to solidify without pressure. The example of the cheap watch industry may be cited to convey an idea of the immensely important revolution which will take place in the production of both small and large prime motors when all the possibilities of electrotyping, casting and stamping the various wearing parts, true to shape and size, have been fully exploited. An accurate timekeeper is now practically within reach of all, and in the 20th century no one who requires a small prime motor to do the rough work about home or farm will be compelled to do without it by reason of poverty, unless perhaps he is absolutely destitute and a fit subject for public charity. Many domestic industries which were crushed out of existence during the early part of the 19th century will therefore be resuscitated. The dear steam engine created the factory system and brought the operatives to live close together in long rows of unsightly dwellings, but the cheap engine, in conjunction with the motor driven by transmitted electricity, will give to the working people comparative freedom again to live where they please, and to enjoy the legitimate pleasures both of town and of country. End of chapter 4.